This lecture I'm going to cover about crystallization. Yeah? So that's the topic I'm going to talk today. I know in the first week I was talking about liquid extraction. I will continue that in week 3. But why I decided to take this topic for week 2 is like I already posted the video about your lab that deals with how do you integrate your pad tools with the crystallization unit, and then I will. The plan is to. I already did the experiment. I already have the experimental data with me. It's a very laborious process. It's like each experiment took roughly 48 hours. So this 48 hours includes to clean the reactor, clean the pad probes, and then I have to optimize the pad probe. I cannot just like that add all those pad tools and then start the experiment. I have to adjust a bit, a tweak here and there, and then calibrate all the pad tools before each experiment. And then I have to prepare the samples, and also I have to wait. Sample preparation time itself, it takes a lot of time, and then I have to dry the crystallizer because crystallization is such a such a tough experiment. It's not easy to go to lab, mix some things, and take the crystals out. That's no way when you are going to deal with the crystallization experiment. Everything should be extremely clean, like any biological process. You should pay the same level of attention or details to the experiment, like in terms of cleaning the reactor, drying the reactor should be free of any impurities or even dust particles, because all of those things will affect the experimental outcome of any crystallization experiment. Yeah, not only the one which I posted in the YouTube already for you. So I think I know the class, we have a mix of chemical engineering, and we also have students from pharmaceutical chemistry and also graduate diploma on chemical engineering. And I designed that particular experiment keeping pharmaceutical chemistry students in the mind. They cannot leave this module without knowing about pad tools, because that's the something which is going to get them the job in the industry. And if you look at the video, the lab video, few places I already mentioned that there are no companies or industries at the moment, especially in Ireland, who without relying on pad tools. Yeah, like if it's not only about crystallization, like the like tableting process, for example, even for that they use pad tools. So pad is becoming, it's not a fashion or a buzzword. It nowadays it's becoming an essential tool. So it's, and every industries are trying to find a way to integrate it with the existing technology. And obviously they, at the moment they do not have enough experts who are familiarized with the pad tools, or even have the basic knowledge, theoretical knowledge, or if they have practical knowledge, it's even better for them. So PAT is a big educational issue in Ireland, yeah, especially for pharmaceutical chemistry students. It's absolutely a must in your CV. So that's why I took this effort to create that lab video. That lab video, I might have done some mistakes here and there. I got permission only for 4 days to work in the lab. I planned this experiment for the last year students, but due to COVID I couldn't implement. So this year I don't want to miss that. So I I thought, if I cannot take you to the lab, at least I should put some virtual lab, something like the one which I tried. So this is like my first attempt to take pad tools to the chemical engineering and also pharmaceutical chemistry classrooms. I already showed you how to do the experiment, but before it, I know some of you already watched. I saw the number of views in the YouTube, but to understand the process of crystallization itself in a better way, you should have some theoretical knowledge on the process of crystallization. So that's why I decided to spend some time this week on to explain the basics of crystallization. So if you look at your book of modules, crystallization play, you have a separate chapter on crystallization. So what I'm going to do is, like, I will cover this crystallization completely in this week. If I manage to finish, I will then it's good. If not, I will continue a bit in week 3 as well. So I will try to finish the crystallization so that you will have enough time to know what is crystallization. You would have already, you will understand what this crystallization is about, and that will help you when you are going to write the lab report and assignment. When you are going to submit the lab report and part assisted crystallization, it's not just the lab report, it is like an assignment plus lab report. So I'm going to just explain what I want to talk about crystallization, and then I'm going to scan and upload the notes in Sulis. Yeah, and you need this theoretical knowledge to in order to interpret the experimental data which I'm going to send it to you. Yeah, so and also you should know what is crystallization is all about, and especially if you are a pharmaceutical chemistry student, so crystallization is a must topic to learn, because almost 90% of the active pharmaceutical ingredients are are purified using crystallization technique. In fact, I believe they might have used crystallization at least 4 to 5 different times, yeah, in order to get a pure product of most of these active pharmaceutical ingredients. So it is essential to have some knowledge on that. And also I will also try to okay, I can mention which book to read. John Mullen. So that's the book I'm following for the last 10 years to learn about crystallization, and that's the book I'm using at the moment as well. But this lecture notes will look like not like book not will not look like a textbook material, but it will look like a more like a sharing the personal experience, yeah, in the lab. So I am working in this field for last 10 years. So in fact my second PhD is in crystallization. So I'm going to give the extra bit of details that you may not find in the textbook. But if you want to follow some textbooks, so that's the book you have to use. John Mullin. It's a very very good handbook. Many crystal engineers and also crystallization scientists, they consider this book as a Bible of crystallization. So that's enough introduction, and then I'm just going to say like what are the topics that we are going to cover in this particular lecture. And these are the topics that you need to understand to know a bit about crystallization, and also you will need this knowledge when you are going to interpret your experimental data, and even to know like if you look at the YouTube video, what I uploaded is like I crystallized a paracetamol. I put some experimental conditions, and then why I chose that experimental conditions, and why I grow crystals at 20 degrees centigrade, why I fixed the supersaturation ratio of 1.2. So that's the experimental conditions I used in the video which I posted in the YouTube. So I did the experiment at a supersaturation ratio of 1.2 and a temperature of 20 degrees centigrade. That's my working temperature. I used an agitation speed of 350 rpm, and I performed 2 different experiments. So first experiment, I have a seed loading of 50%, and second experiment I have a seed loading of 80%. So if I ask you to write about this, you will go crazy, because you don't know what is supersaturation ratio of 1.2, why I choose supersaturation ratio of 1.2, what's the meaning of seed loading, what do you mean by that, like 50%, why do I even increase the seed loading to 80%, what's the point about that. So to answer all these questions, you must know the basics of crystallization. So that's why this week I switched the topic from liquid extraction to crystallization. So I'm sorry for that, for changing the topics from like moving from liquid extraction to crystallization. But don't worry, I think this is the right way to go, because I don't want you to stress you like showing some video for 1.5 hours and ask you to write something very good report out of that without giving you the essential knowledge that you should know, or that you should need to understand the topic. Yeah? I mean the laboratory exercise topic. So I will just quickly list out what are the topics that we are going to cover. So one is like I will talk about driving force required for crystallization. Then I will talk about solubility. So whenever we talk about crystallization, you must think about solubility. So crystallization means you should think about solubility. You cannot talk about crystallization if you have no clue what is a solubility. So that's the first information you need before to start a crystallization experiment, before to even understand why crystals grow. Yeah, if you want to look a crystal as an art, then you don't have to think about solubility. If you want to think crystallization as a science or engineering subject, then you must know what is a solubility is about. And then I will talk a bit about supersaturation. And then I will introduce you what is a metastable zone width. So metastable zone width. I think this video is going to become bit lengthy because I'm writing. I'll try to write bit less because I'm going to upload anyway the notes for you. I will scan my notebook and then I will upload it to you. And then I will introduce you what is a primary nucleation. And then I will tell what is secondary nucleation. What is secondary nucleation? And then what can we do? Like just to mention here, since this metastable zone width, why are we studying this is like many industry people, they call this as a crystallization treasure map, and we will connect the concept of primary nucleation and secondary nucleation with this concept of metastable zone width. So that thing we will cover in this lecture. And then you are going to learn a bit of theory. So I'm not going to load you with some heavy duty mathematics, but you must know something really basic about crystallization. So for that you should know something called as Gibbs free energy. Everything connected to crystallization. So Gibbs free energy from the viewpoint of crystal growth science. This Gibbs free energy, this will be a bit toughest part for you to understand, but for that you need a extra bit of imagination. So I will try to draw some figures and maybe try to put it in a simple way so that you will know what is this about, like you have a solution, some crystals form from the solution out of nowhere. So why it's happening? For that you need to, or why is that happening? Or if you want to give some theoretical, like if somebody asks you why crystals form in the solution, then you can tell them in a very scientific way, but to give that answer in a scientific way, you should know what is something related with Gibbs free energy. Yeah? So we will come back to that topic later. And then just a note, like crystallization always produce very beautiful crystals, yeah, so of different shape and size. And doing an experiment is very simple. All you need is to go to a lab, make everything clean, add the reactants, add the solvents, and know a bit of theory, and then you can make a nice crystals out of that. But it's a very tough concept to understand, like to expose the crystal growth mechanism. That's really a tough business. Many people are trying for last 100 years, and most of the knowledge that we have in crystal growth science or in general crystallization are mostly hypotheses. So and we can call it like a scientific hypothesis, and rather than like actual scientific finding that comes from experiment, like based on some some experimental evidence. Yeah? So try to keep that in the mind. So throughout this lecture, I'm going to draw some pictures. I'm going to ask you to imagine that's how the molecules looks like. They might like to come together. They may disappear again. They might form into something like a cloud, and then they might settle into some crystals and so on. So you have to imagine all these things. That's the only way to understand the topic of crystallization, and that's the only way you will realize why crystallization is called as a purification technique. So but anyway, we will come back to that later. So these are the topics I am going to cover in this particular lecture. And then few more things is like and you must know like so if you have a solution, you have some molecules, they assemble into crystals. The mechanism happening in between, it's very tough. Not every lab in this world have the facilities to monitor at something at molecular scale. Yeah, so your crystallization mechanism itself is tough, but we are going to cover some of the scientific hypotheses that can explain what's happening in between from solution to crystal. So these are the topics that I will cover in this lecture, or maybe in the next lecture. And then what else we can see? And then time to time throughout the lectures, I'm going to show you how the industries are exploiting this crystallization technique, what type of experiments or processes or what type of trials they perform when they decide to manufacture a product using crystallization technique. Not manufacture in particular, when they decide to purify a particular product. And then I will go back to time to time I will go back to the lab topic. So once I finish some theory, and then I will try to connect it with your lab topic, which deals with the crystal growth of paracetamol. And then time to time I will tell why industry people grow the crystals using different set of protocols. Yeah. So this video is about this video, and probably the next video is all about probably I will cover the topic for 1.5 hours. So I will mostly about how crystallization works and the basic concepts in crystallization, and then I will put another half-an-hour video on what's your experimental how do you call it, what the laboratory experiment is about, like what are the experimental conditions I fixed, and what are the data I'm going to supply, how you have to look at the data, and how you have to process your data, and how the report should look like. So that will be like a half-an-hour video. So you will first learn the crystallization theory, and then you will take some experimental data, and then you apply your theoretical knowledge on those experimental data, and then you make a nice report. So this is like a nice way to learn, like through the practical knowledge. Yeah? So you will see you will from the video you will know how to perform the laboratory experiment. So let's go to this topic, crystallization. So crystallization is a purification technique. It's a purification technique. The main objective of crystallization is to purify some compound. Obviously, it's an unit operation, and it's widely used in pharma and food industries. Yeah, so these are the guys who mostly use food in the crystallization technique. As I said, many of the APIs in the market must have gone through several crystallization steps. And one more thing, crystallization is purely a mass transfer process. Purely a mass transfer process. And it's purely a physical process. So there is no chemical reaction, there is no chemical, there is no bond breakage, there is no new bond formation. You are not degrading anything. Whatever the molecules that you are going to add into the crystallizer, it's going to remain intact. So there is no change in the chemistry. So it's purely a physical process. So keep the word unless specified. It's purely a physical process. So especially in pharma industries where they are going to use crystallization mainly for purification purpose, it's purely physical process. There are some few process, we call it as a reactive crystallization, where you might expect some bond breakage and bond formation. Two atoms, they come together to make a new molecule. So we are not going to cover that one. And especially pharma industries, they really don't care about this topic, yeah, like reactive crystallization. For the people who do not have an engineering background, I'm just going to explain what is a mass transfer process, yeah? Or something bit about a mass transfer. So imagine you have like two compartments where you have your salt solution, for example, say just a normal table salt, sodium chloride, and you have a pure liquid, pure water in the other side. Just assume for the moment we have something that can separate these two compartments, and just assume you have a small hole that allows you to to transfer your molecule from your left compartment to the right compartment. So once you just open this tiny valve, what will happen is like the salt will move from this compartment to this compartment. And why that happens? That happens because there is a concentration gradient. So you have a high concentration zone here, and then you have a pure liquid here. So imagine you have like a 20 grams of your salt dissolved in 1 liter of water here, and here you have a pure water. So the concentration gradient is 20 grams per liter. So what will happen is like the salt will move from high concentration zone to low concentration zone, which means some mass is moving from one spot to the another spot, say from point 1 to point 2. So that's the principles of mass transfer. For the mass transfer process to happen, you need some driving force, and that driving force is nothing but concentration gradient. And mass transfer is purely a physical process. So all we are doing is like we have some molecule here, say location A, and then it moves from location A to location B. So it's just like a transport of mass from one side to another side, and this process is driven by a concentration gradient, and your molecule will remain intact. There won't be any chemical reaction, so it's purely a physical process. So these are the things you should remember about mass transfer. And one more thing you should know is like a mass transfer is like a one-way process. So it goes from one side to another side. So it goes from high concentration side to low concentration side. The handwriting might look bad, but you don't have to follow these notes. Yeah? So all I'm going to do is I'm just going to explain the different topics, and then I'm going to scan and upload the notes, which is easy to read. And just imagine you have a probe here, say a conductivity meter here, and another conductivity meter here. So this is your compartment 2, and this is your compartment 1. So this is compartment 1 and this is compartment 2. And then we monitor the change in concentration with respect to time. So if we plot time versus concentration, so this is your 20 grams per liter. So this is the one from compartment 1. And if you monitor the concentration of the salt in the compartment 2, it will go something like here. Yeah? So the concentration in this compartment will increase with respect to time, and the concentration in the compartment 1 will decrease with respect to time, and eventually at some point they will reach to saturation, or we call it as equilibrium point. So at that point, at this particular time, say this happened in 1 hour, so if you put a conductivity meter on any location in any of these compartments, it will read the same concentration. Say it reached around 10 grams per liter. So that's the point of equilibrium. So mass transfer is a purely physical process driven by a concentration gradient. It's a one-way process. It goes from high concentration zone to low concentration zone, and this process continues until the system reaches to an equilibrium. So this is more than enough for this particular module, especially if you do not have an engineering background and if you haven't learned anything about mass transfer. All you need to know is like what's mass transfer and how it works and what's the driving force required for the mass transfer process to happen. I have to cover this topic because not only for crystallization or because you need to know what's the mass transfer process when I'm going to explain about adsorption, crystallization, distillation, liquid extraction. So, and we need to cover all these topics in these modules, and you will not understand anything unless if you don't know what's mean by a mass transfer. Yeah, so mass transfer is not like a tough topic to understand. It's extremely easy, and there is no chemical reaction. So it's and all you need is to know is like something goes from one side to another side, and this happens naturally due to some driving force, and that's called concentration gradient. Yeah? So that's enough about mass transfer. So just to take this part as like an introduction to mass transfer, that's more than enough. And this the rule of mass transfer, like something goes from high compartment to low compartment zone, that rules apply even if we deal with solid liquid. So in adsorption we will deal with solid and liquid, and crystallization we are dealing with solid and liquid, and then distillation we will deal with vapor and liquid, and then in liquid extraction we will deal with liquid and liquid. So irrespective of the systems, the definition of mass transfer remains the same. Yeah, so keep this in your mind, because I'm not going to repeat anything about mass transfer in the next lectures. Yeah, even when I'm going to talk about adsorption or distillation, I will just use this word again and again, like this is happening due to a mass transfer process. Yeah, so try to get this basic knowledge or idea about mass transfer. So now let's go back to the topic of crystallization. So before talking about crystallization, you should know something called as solubility. So I'll quickly explain what is that. So probably you might have known, you might have read this in some other modules. It's really basic. So what we have here is like let's call this as a crystallizer, and we have some jacket to heat, and then we have an API compound, active pharmaceutical ingredient. So say we have like a 20 kilograms. So let's add into this one, and just assume we have 1 liter of some solvent, say water. So this is your solvent, and then just assume we have some UV spectrophotometer here, so that allows you to monitor your concentration expressed in terms of grams per liter. So what we are going to do is like we are going to plot the temperature expressed in terms of degrees centigrade versus your solubility concentration. So we heat the solution, the solution to 5 degrees centigrade, and say let's wait for 8 hours or maybe even 24 hours. So which means during this time some amount of your API will get dissolved. Say we dissolved roughly say 4 grams per liter, and then you continue the process again. You heat the solution back to 10 degrees centigrade, say we dissolved 8 grams per liter. So this is 5, this is 10, and then we continue the process. Yeah, so say at 40 degrees centigrade we managed to dissolve all the 20 grams per liter. Yeah, so if you plot a curve, you will get something like that. So we call this as a solubility curve. So why are we talking about solubility? So solubility is something like solubility is a concentration that measures how much, like the maximum amount of that compound which you can dissolve in that particular solvent. So that's how you define a solubility concentration. So why do we need to know this value, solubility concentration? Yeah, because we are dealing with the crystallization topic, and I already said to you what is a mass transfer process. So you need a concentration gradient, but when we need to crystallize something, we just the concentration gradient is not enough. Yeah, you need something more than that. It's called supersaturation. So the driving force for crystallization is supersaturation. So always remember, whenever you think about crystallization, you must think about supersaturation. Supersaturation, solubility. I know that I just now I said when like during mass transfer something moves from high concentration zone to low concentration zone. We call this as a diffusion process in chemical engineering. If something moves from high concentration zone to low concentration zone via due to a concentration gradient, we call it as like a diffusion process. But to crystallize, you need something more than this driving force. Yeah, we need something called as a supersaturation. Yeah. So let's go back to the solubility curve. So temperature, I'm going to use the notation C star grams per liter. So C stars mean solubility concentration. For any API, you can generate this solubility curve. It's very easy to do this experiment. So just imagine you have some API and that's your solubility curve. So that's your solubility curve. Wow. So I'm just going to say what happens. Yeah? Like just repeat this experiment. Say this time you added 40 grams per liter, 40 grams per liter, and imagine you heat your solution up to 40 degrees centigrade, and your solubility concentration is 20 grams per liter. So which means you cannot dissolve more than this amount at 40 degrees centigrade. Yeah? So your C star at 40 degrees centigrade is 20 grams per liter. So no matter, even if you remain for 1 year, you cannot dissolve more than this into the solution. And why is that? Because your solution already reached the solubility limit, which is 20 grams per liter. So if you started your experiment at 40 grams per liter, your solution will look very turbid. Your solution concentration will read 20 grams per liter, and your solid concentration inside will be equal to 20 grams per liter. So what it says is like what we can understand from the solubility experiment is like the solid phase will remain in the solution once you reach the solubility limit. So that's the take home message. So that means solid phase can exist in that solution only if the solid concentration or the solute concentration is above the solubility limit. Yeah. So which means if you have a solution, if you have to crystallize something, so crystals are nothing but solids. So if you have to make some solids, we need a concentration in the solution, which should, at least we should start the experiment from a solution that have a concentration which is higher than the solubility limit. So that's the key message that you should take home. So we need a solution to in order to initiate crystallization or to create a solid. It don't need to be crystallization. If you want, you can call it even as a precipitation technique. Yeah? So if you want to create, just assume this is a pure solution, and if you want to create new crystals into that solution, you must have the concentration. The concentration of the solution should be must be greater than your solubility concentration. So which means we need something, we call it as a supersaturated solution. So supersaturated is a solution that contains your solute, or the concentration of your solute will be in excess to that of your solubility concentration. So we call such solution as a supersaturated solution, and we need supersaturation in order to create a solid phase. Yeah. So that's the take home message. So how to create a supersaturated solution? So to create a supersaturated solution, let's plot the solubility curve again. So temperature degrees centigrade, your solubility concentration expressed in terms of grams per liter. Let's draw some line. Let's call this is your solubility line. So let's say at 20 degrees centigrade your solubility is 20 kg. Say at 40 degrees centigrade your solubility is 30 kg, and then at 50 degrees centigrade, so this is your 50 degrees centigrade, and your solubility is 45 kg. So if you connect these lines, these dots, what you get is called as a solubility line. You cannot crystallize a compound unless if you have the solubility data. Yeah? So any industries who if they want to purify a compound, the first thing they do is check for the solubility data. If they couldn't find it in the literature, they will do this experiment in order to get the solubility data. Yeah? So that's the first thing they do. If you apply for a job like a crystallization scientist, then they will ask you a lot of questions about how do you measure solubility, what's the concept behind solubility, what do you think about supersaturation, and many things. What are the different techniques available to get the experimental data on solubility. Yeah? So that's why it's really important. So I will tell. So even if you want to crystallize a compound, you need to create a supersaturated solution. To create a supersaturated solution, you need solubility data. Yeah? So I will tell you what we do in the lab to create a supersaturated solution. So what we do is like just let me change it to highlighter. Just look at this point here. So and point here. So at 40 degrees centigrade, we know we can dissolve. The solubility is 30 kilograms per liter. Yeah. So this is per liter of your solvent. So let's write that one. So at 40 degrees centigrade, your solubility is 30 kilograms per liter. 30 kilogram. So what we do is like we take a crystallizer, we add 30 kilograms of your API, and then we add 1 liter of your solvent. Obviously, if you are going to work with 500 milliliter, then we have to add 15 kg of API. So probably we will try to solve some problem, so you will know how to convert the units depending on your reactor volume. So this is what we do in the lab. So assume this is your crystallizer. So we already added 30 kilograms of API. We added 1 liter of our solvent. So we know that, so this is, if we heat it to 40 degrees centigrade, which is here, the solubility point here, we can dissolve almost everything, 30 kilograms in 1 liter of that solvent. Yeah, so 30 kilograms is a lot. Yeah, let's put it like a 30 grams, 20 grams, 45 grams, something like that. Yeah, so but what we do in the lab is like we add 30 kilograms and then we heat the solution. Instead of 40 degrees centigrade, we heat the solution directly to 50 degrees centigrade, which is here. So that's your 50 degrees centigrade. If you come down, that's your 50 kil. We know that at 50 degrees centigrade we can dissolve 45 grams per liter. So which means at 50 degrees centigrade for sure you dissolved everything into that solution. So 30 grams per liter. So what it means, like we heat the solution like 20 degrees above the solubility temperature. So by the way, if you want, you can call this temperature 40 degree as a solubility temperature. Solubility temperature, or if you want, you can call it as a saturation temperature. That's the right word, in fact. So saturation temperature means like a temperature required to completely dissolve a known mass of solute in a solvent. Yeah? So that's the definition for saturation temperature. So let's go back to this graph. So what we do is like we go to 50 degrees centigrade, which means we already dissolved everything. We just to ensure everything is completely dissolved, and then we cool the solution back. We will cool it slowly. Say we come up to 20 degrees centigrade until this point. Just follow the green line. So we cool it back to 20 degrees centigrade and just assume that solution remained in liquid phase. Yeah, so that is no formation of crystal until this point, nothing precipitated. So the solution remains like a solution. Yeah, so you come to this point. So we all know at 20 degrees centigrade the solubility concentration is 20 grams per liter. Yeah, so at 20 degrees centigrade the solubility concentration, wow, let me change. So at 20 degrees centigrade the solubility concentration C star is 20 grams per liter. But however, we have at the moment in the reactor we have 30 grams per liter. So this type of solution we call it as a supersaturated solution. We call this as a supersaturated solution. And if you want to calculate what's the level of your degree of your supersaturation, there are few definitions, or how do you call it? You can few expressions. There are different ways to express your supersaturation. So one easiest way is to define like a ratio. We call them as a supersaturation ratio, yes, which means supersaturation ratio. S is equal to C by C star. So in this case, your concentration of your solution is 30 grams per liter, and then your solubility concentration is 20 grams per liter. This is at 20 degrees centigrade. So why does we cool the solution back to 20 degrees centigrade? So we are going to call this as a 20 degrees, like working temperature. Yeah. So let's call, we stopped the cooling process at 20 degrees centigrade because we are planning to do something at 20 degrees centigrade. So we are going to fix that temperature as working temperature. So whenever you think about crystallization, just think about these terminologies: solubility, solubility concentration, supersaturation ratio, saturation temperature, and then what else, your working temperature. So these are the things you have to comes into mind. And then when you're thinking about creating supersaturated solution, we need to heat the solution 20 degrees above 20, or some temperature. I just keep it in how do you say, like this. Just want to highlight here again this particular point, like 40 degrees centigrade. There is no rule like we have to heat it to 50 degrees. We can heat like 40 degree plus 5 degrees centigrade, or 40 degree plus 10 degrees centigrade, 40 degree plus 20 degrees centigrade. So we are providing that extra bit of temperature just to ensure all the solids which you add into the crystallizers are completely dissolved. Yeah. So these are the things that you should remember in your mind, because that's what I did in the lab, and you have to include these experimental details in your laboratory report. And probably we might solve few problems. You might expect some problems in the final exam from crystallization. So try to pay attention to all to these simple expressions and some terminologies. And I might even ask in the final exam, like I need to crystallize some compound at 20 degrees centigrade, and that's the solubility curve you have. Tell me the experimental procedure, how you are going to do that in the lab, or even in industrial scale reactor. Yeah? So you have to write something on that line. Yeah. So in the exam you might have some lot of open-end questions, and this is one good questions to ask in the final exam. So try to remember how crystallization works, and how to perform the experiment, and how do you maximum you exploit the solubility data. I have to go this topic very slowly because it's tough to grasp, like, because our human mind is so used to play with concentration versus time. You might have learned a lot about first order kinetics, second order kinetics, reversible reactions, irreversible reactions, probably in general chemistry. But when you talk about crystallization, you have to come out of your comfort zone, which is concentration. You have to talk everything in terms of supersaturation. If there is no supersaturation, there is no crystallization. Yeah. So that's why I'm going a bit slow. Okay, coming back to this topic. So that's how you define the supersaturation ratio. And then there are few other ways to express supersaturation, like sigma, delta C. We will come back to this. Probably we will solve some small exercise problems. I will ask you to convert your supersaturation. I will give you some concentration and solubility value, and then I will ask you to calculate S, sigma, and delta C. So you have to calculate it for me. So that's how we create a supersaturated solution. I hope you all can understand. I'm just going to repeat how to do one more time. So you have 40 degrees centigrade, 20 degrees centigrade. You add 30 grams per liter, which is the solubility concentration at 40 degrees centigrade. So we heat the solution to 50 degrees centigrade, and then we cool back to 20 degrees centigrade. So this way, at 20 degrees centigrade, the concentration will be above the solubility concentration at 20 degrees centigrade. And then from there you can calculate your supersaturation ratio. And then I talked, you should remember what is a working temperature. And then saturation temperature. Saturation temperature. Saturation temperature is this particular point. Yeah? Let me change this color. Saturation temperature is this one, 30 degrees centigrade, T star. And your working temperature is 20 degrees centigrade. So that's how we create a supersaturated solution. So let me change. So what we learned so far is like we know how to perform a solubility, and another thing I forgot to emphasize that's even extremely important is this one. If you look at the trend line here, so what it states, just to follow the arrow which I'm drawing now. So you have temperature here, and then you have your solubility concentration. So another thing that you must remember is like, okay, why it's like this? You have your solubility concentration grams per liter in the y-axis, and then in x-axis you have your temperature. Yeah, so this one. So what you see from this graph is like your solubility increases with temperature. So that's why we are cooling the solution in order to create a supersaturation. Yeah? So if your solubility is going to decrease with temperature, we have to do something else to create a supersaturated solution. So the rule is like a solubility will always increase with the increase in temperature. So these are the things we learned. So what we learned so far is like solubility line, solubility concentration, solubility line mean how the trend looks like, yeah, like C star versus temperature. And then what is a solubility concentration, and then we know what is supersaturated solution. And then I said to you, from the simple solubility experiments, we already know that above your solubility limit, the molecules will, or your compound will remain in solid phase. So that's another thing that you learned from this, I don't know how to call, like a lab on a paper maybe, like this simple experiment that we are thinking at the moment. Like if I'm going to do a solubility experiment, that's how I'm going to do. I'm going to add some API compound in the solvent, and then I'm going to monitor the concentration, and so and so on. The key thing that you have to remember, yeah, how to draw the key. Yeah? So one fact that you should remember again and again is like above the solubility limit, above the solubility limit, the solute molecules just say it, yeah, like solute molecules will not like to stay in the dissolved state. So the molecules which are present in excess to that of solubility concentration, they will come together and then they will make a solid phase. So what do I mean by that? So imagine if you were at 20 degrees centigrade, and then if your solubility concentration, say for example, is say 20 grams per liter, and then if you have some, say these dots are your solute molecules, So this will remain in solution forever, yeah, even if you leave it for 1 year or 2 years. But if you have a supersaturated solution, 20 degrees centigrade, so again we have some solute molecules, and then if we have something, if your concentration is greater than your solubility concentration, say 40 grams per liter, and we know the solubility concentration is 20 grams per liter, so the difference between them is 20 grams per liter. So the molecules that make up this 20 grams per liter, they like to come together and then they like to form solids. So eventually it look like you will have a solution with a concentration of 20 grams per liter, and your solid concentration will be 20 grams per liter. So that's the theoretical fact. So that's how solid and liquid equilibrium works, yeah. So you cannot dissolve anything more than the solubility limit, and if you have something more than the solubility limit, then the molecules which is dissolved in excess to that of your solubility concentration, they will try to figure out some way to come together and precipitate together and settle into some solid form, yes, into a solid state. So that's the theory. You have to keep it in your mind, you know. But that's one theory, you have to keep it in your mind, and always remember there is a room to make a supersaturated solution where your solution concentration can be above your solubility concentration, and still you will not have any solid particle in that solution. So if you know these two, you cracked 90% of the crystal growth problem, yeah. So if somebody asks you to purify an API compound, if you know these two concepts in your mind, you will know how to purify a compound, and you will know how to perform a crystallization experiment. So try to keep these things in your mind, yes. And then I want to show you something that you have to imagine at a molecular level, yeah. So let's see this very quickly. So just assume this is your solution, and then we have some, how to call, so this is your saturated solution. So this is your supersaturated solution. So let me choose some color, yeah? So this is your solute compounds. Just imagine it contains two atoms that making one molecule. So they are randomly distributed in the solution, yeah. So when it comes to supersaturated solution, you will have a large number of your solute molecules, because your solute molecules or your solute concentration is in excess to that of your solubility limit. So you will have loads and loads of your solute molecules, and that's how it will look like. If you have really some molecular level microscope, the solution will look like something like this, yeah. The molecules will jiggle around and they will randomly move within its space. So that's your supersaturated solution, yeah. So once you have, if you have your saturated solution, so everything will move randomly and everything will look intact. But when you have a supersaturated solution, you have a lot of your molecules which is in excess to that of your solubility concentration. So what they will try to do, which means your energy is extremely high, yeah. Like this is how do you call, even if you want you can call it like a frustrated state, like so many molecules, they are confined into small space. It's something like you are squeezing too many molecules into a small space. So they will try to come to a comfortable state, which means they will try to minimize some energy. So, and how they will do is like so after some time, what will happen is like these molecules, they come together. So they will come together here and there, and that too they will come in such an orderly fashion. Yeah, so if you put a box around that, it will make a crystal. So this process will happen until your concentration reaches your solubility concentration. Yeah, so while your other molecules will remain in the solution. So that's what happened during a crystallization, and that's how you have to think about a crystallization process. Yeah, so you get normally a beautiful crystals at the end of the day during a crystallization, but that whole crystals, the formation of crystals, everything started from this small step that happened at molecular level. Yeah, so you have to remember these things. If you don't get a picture at that molecular level, it's very difficult to understand how crystals grow out of nowhere from solution. Yeah, so you are making a new solid, something like the solution is giving birth to a new solid, and there is a reason for that, and that's because you have a supersaturated solution. When you have supersaturated solution, you have too many molecules which is in excess to that of your solubility concentration, and they likes to come together and they will settle together. They might form something like a solid, and eventually at one day or some time it will get into a solid crystal. Yeah, so that's the whole principle behind the crystallization technique. And this one I just draw a diagram and just mention the word just like that after some time. So this time there is a technical meaning or a technical term for this one. We call them as a lag time. Many researchers call this as an induction time. So during this induction time is the time at which all of your molecules in your supersaturated solution, they try to meet each other, they try to recognize each other, and they try to realize how to fit with each other, and then they will come together. They might even form something like clusters. Some people call it as intermediate phase. So imagine like if you have some molecules like that, randomly they will come together. They will randomly come together. See, they might look like a blob, and then they will eventually assemble into a perfect crystal. So some people call this as cluster, some people call this as intermediate phase. So this is your stable particle. This is your stable particle. Usually it is crystalline. And since this is your stable particle, whatever happening, something that might look like some structure, we call them as a metastable. Metastable solids maybe. So these are the things you have to remember about crystallization. So I know chemical engineers must have studied crystallization in some of their modules. So whatever I'm covering now, I'm sure it's not covered in any other modules, even if they might have learned crystallization. So I try to cover crystallization topic purely from science viewpoint. So you might not find this in classical textbooks. Yeah. So one day I will try to convert this into some lecture note, or maybe like a book, probably next year. But whatever I'm saying to you, they are extremely correct. But if you go into some hardcore scientific literature, you will get this information. So these are not wrong information. They are absolutely right, and that's how crystals grow in the solution. So I think this is more than enough to give you some idea how crystals grow in the solution. Because if you go to classical textbook, even the Mullin book, which I really love to read, so they will talk about this, what is saturation, what is supersaturation, what is solubility. They will suddenly jump into metastable zone with, and then you have to and you will never know what are they, like you will have that textbook knowledge, but you will never know why do I create, how do I create solubility, and what's the point, sorry, why do I create supersaturation, and what's the point of creating supersaturation, and why crystals appear out of nowhere from a supersaturated solution, and these things. For that you have to take this type of approach. So what we are learning at the moment is is the basics of crystallization. And then we are trying to understand crystallization at molecular level. Crystallization, what happens is you start from a solution, and then you end up with a nice beautiful crystal, and then we do not have a say one good microscope, for example, that can monitor whatever happening here. So everything that goes from this point, solution to crystal, comes from our imagination. So that's why I repeatedly say this is a tough topic, and you can understand this topic only if you learn through this type of images and extra bit of imagination. and and if you don't realize, if you don't even realize how the molecules assemble at molecular level, yeah, from a supersaturated solution, you will never realize, or you cannot realize, why at the end of the crystallization we get a pure product. We will come back to that very soon, but to 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 get that type of understanding, you should know why, how molecules assemble from in a supersaturated solution. Yeah. So so I'm just going to say you should have two key or two basic ideas or knowledge. So the first one is you can create a solid phase in solution only if you have a supersaturated solution. So that's first thing you have to learn. And then second is solvent will continue to accommodate a solute when your solution concentration is less than your solubility concentration. So if you want, I can draw a picture to explain what do I mean by that. If you have an undersaturated solution, you just imagine, let's use this green. These are your solvent molecules. Have these solvent molecules, and then you suddenly add some of your API compound, say paracetamol, for example. So they will dissolve, and just assume we have so these are your paracetamol compounds, red color ones. So we added the API, say 2 grams per liter, and say the crystallizer is maintained at 20 degrees centigrades. So obviously, and just imagine your solubility concentration, say of paracetamol in this particular solvent, whatever that we are dealing with, say is 6 grams per liter. So which means your solution is clearly undersaturated. So if you allow some time, what will happen is you have your API, your paracetamol compound, something like that, and then your solute molecules will like to build some shell around that. So and that happens due to solute and solvent interactions. Yeah, and the people who are working in molecular simulation, they call this as a solvation shell. So if you have one say change color. So if you have one API like this, and if you have you might sometimes you need 3 3 solvent molecule to make one shell. Sometimes you might need even more solvent molecules. Yeah, so in fact this particular phenomena decides your solubility. So this is how you have to think at something at a molecular scale. Yeah, so I might ask some open-ended questions in the exam on this line, so try to remember it. Yeah, so and then I can give you the textbook information, but I want you to learn all these techniques through this particular module, because when you leave UL, you will have some extra knowledge on this topic when you compare with some other student who's graduated from other university. So you will have some knowledge at molecular scale on the topic of crystallization. Especially you are a pharmaceutical chemistry students, it's better if you understand this topic in a much more detailed way. Yeah? If somebody asks you on crystallization, you can talk a lot based on the events which is happening at molecular level. Yeah? So this is some idea that you should have. So when I say like in undersaturated solution, your solvent molecules try to accommodate your solute molecules. So and that will happen until you reach the solubility limit. And once you reach the solubility limit, the story is completely different. Yeah? I will show you what exactly happens when you reach your solubility limit. So let's sorry. So this is your API compound. So now we are at the something like a supersaturated state, which means we have API molecules in excess to that of your solubility concentration, and obviously the solvent will try to make a solvation cell around each of some of these molecules. Yeah, so whatever the molecules which is covered by solvent, their concentration will be equal to your solubility concentration, and then you will have a lot of left out API molecules here. So what they do is like they will come together. So in this case your solid interactions will dominate. Yeah, so eventually all of your API molecules, they will come together. So your solid interactions will be very high, and then they will settle into a perfect crystal. So what we are learning at this moment is we are learning almost everything about the basics of crystallization, and crystallization is a very important topic, and it is in your book of module, and I'm going this in detailed way. Why is that? Because I'm not going to come back to this topic again. Yeah, so once I finish the crystallization topic and once I finished with explaining your laboratory experiment, that's it. Yeah, so that's all you have to know about crystallization through this module. Yeah, so whatever you are learning is not only about your laboratory experiment, but it's also about crystallization process as a whole. Yeah, what we learned so far is like when you have your solute concentration in excess to that of your solubility concentration, they likes to settle together. The all the solute molecules will come together, and then they will settle into crystals. So keep that in your mind, and now we go back to your solubility curve again. So that's your solubility curve. I hope you all remember the experiment we did just now. So this is your 40 degrees centigrade. So that's your saturation temperature. You must remember what is a saturation temperature, and this is your working temperature, say 20 degree centigrade. In fact, the laboratory experiment which I posted in the YouTube, I performed the crystal growth experiment at 20 degrees centigrade. In fact, I created the solution using the solubility curve of paracetamol. Yeah? So let's do that experiment now. Just like you heat, you add so how much grams, let me remember what we did before. 30, 20. Let's say in this experiment, so we can dissolve 30 grams per liter at 40 degrees centigrade. So that is here. And then your solubility concentration at 20 degrees centigrade will be say 20 grams per liter. So this is 20 grams per liter. So we are going to create a supersaturated solution to work at 20 degrees centigrade. So we know the solubility concentration at 30 grams per liter. So what we going to do is, like, we are going to add 30 grams per liter, and then we heat the solution. Sorry, just to follow the blue line. So we are at 30 degrees centigrade. So we added 30 grams per liter. We heat the solution to 50 degrees centigrade, which is here in this plot. And then let's wait for some time. So once all the solids are completely dissolved, we cool back the solution. So just follow this blue line. So we are cooling back from, let's put the highlighter. So we are cooling back from 50 degrees centigrade back to 20 degrees centigrade, which is at this point, and then you come down. So now at 20 degrees centigrade, definitely we have a supersaturated solution. We have a supersaturated solution, and I already showed how to get the supersaturation ratio, C by C star, which is 30 by 20. So it will be like 1.5. Sorry, it has no units. Yeah. So grams per liter gets cancelled. So supersaturation ratio is 1.5. And just now I said to you through all these images, I said, when you have some concentration in excess, they will try to come together, and then they will make like APA molecules. They will try to come together, and then they will eventually settle into solid. So if that is the theory, why, if you go back to the solubility curve, if that's the theory, why we have a supersaturated solution? Like you are adding 30 grams per liter at this point. Follow the red highlighter, and then we are cooling back. Follow the highlighter again, 20 degrees centigrade. So which means, and then your solution remains in completely liquid phase. There are no solid formation, or there is no crystallization. Yeah, why is that? The answer is it's called the metastable zone width. So the answer is metastable zone width. So now we need to know extra bit of information apart from your solubility line. Let me write it down here. So this is a property of your solute and solvent and your process conditions. I will explain this very soon. What does that mean by this? Like, it's a property of your solute, solvent, and process conditions. So we need to know metastable zone width in order to create your supersaturated solution. So to create a supersaturated solution, you need, the first information you need is solubility, and the second information you need is a metastable zone width. So in the laboratory experiment which I posted, I created a supersaturated solution of supersaturation ratio 1.2, and for that I need to know what is